Hello guys, in today's video. Today we'll talk a bit about transmission lines. Today I want to show you how, based on an oscilloscope measurement, tell the length of the wire and condition of it. Not so much condition of it today, but basically the length of it. So here we have a Cat5e wire, and as you can see it has 4 pairs of 2. So I have twisted those pairs together here, and here I have a small circuit that will be in another video, but it's basically a 1 microsecond pulse generator, because this is the highest and fastest pulse that you can make with 555 timer. It is, for example, useful for HCSR04 sonic distance sensor. So here you see the pulse. As you can see, it's not stable, so the length of it is changing. But the most important part, which is the rising edge of the impulse, is more or less stable. So the first channel of the scope, which is the blue one, is connected to the output of the generator, so the input of our transmission line. Then on the other side, we have channel 2 connected, which is yellow channel. And the yellow channel, as you can see, is delayed. Automatic measurement of the scope says that we have somewhere around 70 nanosecond delay. In my opinion, we have a delay somewhere around 94 nanoseconds. I should say nanoseconds there. And I think that my measurement is a bit more accurate. I used cursor function. And we have delay of somewhere around 94 nanoseconds. So here we have a lab bench power supply, 9 volt DC output that goes into our 1 microsecond pulse generator. Then it goes to the input of the transmission line, and then we have the output. So that's basically the measurement. So let's now go to the theory. Okay, so here's what we have, is how to calculate length of wire. So here we have our Cat5e wire. We have used 2 pairs that were twisted together. On the other side too, we grounded 1 pair, and the other pair is basically with 1 microsecond pulse. Here we have the oscilloscope. Channel A, or channel 1 in my case, is connected to input, and then we connect channel 2 to the output. So here we basically have what we saw, which is a voltage over time graph, and here we have the input impulse and output impulse. So here we have the delay in between, which we will call TD, which is delay time. And to calculate, first of all, in physics you have very simple formula, which is called basically velocity. And velocity is difference in distance over time, over difference in time. So we have difference in time, but we don't have velocity. So in order to know the velocity of our pulse in our wire, this is a Cat5e wire, that's why I've written it there. On Wikipedia we can find that the velocity factor, which is basically a percent of light speed, is 0.64 for Cat5e wire. So basically I calculated 0.64 times c, which is speed of light. Time delay is 94 nanoseconds, which is 94 times 10 to the minus 9 of second. Here we have the velocity factor, which is 0.64 times c, which is equal to 0.29 times 10 to the 9th of meters a second, times obviously our velocity factor, which is 0.19 10 to the 9th meters a second. So we know our velocity and we know our difference in time. So as I said, velocity in a wire is equal to delta r and delta t. So the difference of r, which is a distance, in our case we will call it just a r. The velocity is our velocity, and delta t, which is a difference in time, will be equal to our time delay. So we put it in the formula, and on the left we have our velocity, which is 0.19 to the 10 to the 9th, 10 to the 9. Then we have r divided by time delay. We multiply it by time delay, and then we have all of the numbers on the left side and unknown or the variable on the right side. So we can calculate from this that our wire is 17.86 meters, somewhere around that. Then I was measuring another transmission line, which is a bit shorter piece of Cat5e wire, and same calculations, I was able to tell that it's somewhere around 10.9 meters. So this type of measurement is pretty accurate because the piece of the wire was originally somewhere around 60 meters. Then I sliced it up a bit, so 17.8, somewhere around the result that it should be there. But what if we have some kind of wire and we don't know the velocity factor of it? Then what we need to do is to measure the stray capacitance of a wire, inductance of it, not the resistance. I drawn a resistor here because it's pretty important if you want to know the losses of on your transmission line. But basically you need to calculate or measure the inductance and capacitance. So inductance can be measured with those instructions. So we just need to set a function generator to 1 volt peak, 20 kilohertz sine wave. Then we need to connect parallel inductor to the input of the scope. Then we need to adjust the frequency, so the volt peak to peak will be equal to half of this, so 0.5 volts. And then we plug in the data, the frequency that we will read off our scope, into this formula, or this one if we want to have frequency in kilohertz and inductance in microhenry. Then if we calculated or measured this way the inductance of our wire, the capacitance can be measured with a series resistor here, for example 10 kilo ohm or a bigger one, and then we turn on DC voltage there and we measure what type of voltage we have on the capacitor. But you can just use, for example, I have multimeters and this one has a capacitance setting, and I have another multimeter and this one has capacitance setting too. So just measure a capacitance with your meter and the inductance with your scope. Then we plug it into a simple formula, which is velocity factor equal to 1 divided by C times square root of LC. So we plug in this data into our formula, and we know that the velocity factor of my example transmission line there is equal to 37.25%, which is pretty low velocity factor. Then I was trying to do some measurements with this velocity factor and calculate the delay, and as you can see the length of my wire was 8 centimeters. So I have written there that it's too short and I was not able to properly measure inductance of a wire, because inductance of a wire is obviously not so big like this one, because here I measured 33 microhenry, which is too big.